Hey everyone, welcome to the homework 5 question 1 walkthrough. So we're just going to start right away by looking at the question as always. So we have a large airway lined with a mucus layer of thickness H, and then it lies above a fluid layer, and beating cilia maintain the velocity at the top of the periciliary layer at V0, and it's directed at an angle theta from the horizontal towards the mouth. And we can assume airway mucus can be modeled as Newtonian and neglect the curvature of the vessel and assume rectangular geometry with layer width W and length L. The question is asking us to use the microscopic approach to determine the velocity profile of the mucus layer. Then it's asking us to find the velocity at the luminal surface of the mucus layer. And it's also asking us the flow rate of the mucus in the airway. And it says neglect pressure gradients in the airway. And then also neglect the shear stress exerted by the air on the mucus surface. And then it wants us to derive an equation for the maximum mucus layer thickness. And we can actually look at that question once we get to it. So let's get started. Always the first step is to follow our 6 steps for our shell balance method. And I really recommend checking out the video that I just uploaded on the shell balance approach. It's really helpful and it walks you through step by step. We also are going to be going step by step through this process. So let's start with step number 1, which is to define the shell. So let's just take a look at the diagram once again. We have the mucus layer right here and the periciliary layer right here. And then looks like you can see it faintly, but we have velocity 0 right over here. That's V0. And the great thing also is we have X and Y components right here. And it's also slanted at the theta angle right here. So it really helps. We only have to look at one of the components because we have fluid flow in only one direction, right? So that's great. Also, please note that we're going up. So we have velocity 0 at this layer, but then we also are fighting gravitational forces there. Great. So that means, actually, sorry, we're going to take a look at this again. We're going to model the shell. We can see that we have X and Y components, and essentially we want to include those in our shell. So we have essentially a small volume box right here. And throughout this process, where I'm going to talk about how we're trying to actually make this shell as infinitely small as possible. So with that drawing right over here, I'm just going to redraw it out here. But essentially I drew a box and we have in the X, and then we have X plus delta X. And then we also have Y right here. And then we also have Y plus delta Y. So this is our shell. One thing to also keep in mind is we have a width W. And this is essentially not just the 2D box, but it's actually kind of a, not a cube. We don't know that it's a cube, but it is a box with volume. Great. So essentially this is our shell. I'm just showing the 3D version with width along with it. So there's our shell. Let's move on to step number 2. Step number 2 is apply conservation of mass. Great, so we know that conservation of mass is defined as dm dt equals the mass flow rate in minus the mass flow rate out, and then mass flow rate due to the wall. We know that through conservation of mass, we have 0 accumulation of mass flow and 0 mass flow from the wall. So that can be simplified to 0 equals W in minus W out. Great. That also means, let's keep going. We have rho Vx times the cross-sectional area. What is the cross-sectional area of flow? Well, we know flow goes from here to here. So that means we have right over here is width, and then right over here is delta y. So we know this is the cross-sectional area, right? And then that's the same over here as well. So we know, I'm actually going to erase that so it doesn't get too confusing. We know the area, the cross-sectional area is delta y times width. And then we also know this is at x. Then we want to subtract the mass flow rate out. We have rho velocity, and this is at x plus delta x, right? Right over here, this area right there. And then we also have that times delta y times w. Great, so if we actually simplify that further, we are going to first divide by the area, the volume, volume of our shell. And this is really similar to pre-lecture notes 1. Please take a look at how we do derive conservation of mass and how we go about that. So please take a look if you are confused. But here we are going to first simplify. I'm going to actually pull out the Vx terms. Then we have this times delta y times w times rho. Right? Great. So then we're going to actually take, divide by the area, the volume, and we'll see that we have this. We have this right here. Great. And why are we taking the limit? Well, because the actual approach, the shell balance approach, is asking us to determine a shell instead of the entire system, right? And our goal is to make that shell infinitely small by taking the limit. And when we also take the limit of this, we know that this actually is, this is the negative derivative. You can see that the terms in the numerator are swapped. So that essentially is just the negative derivative of Vx times rho with respect to x. And we also know rho is constant, right? And so since we know rho is constant, we can actually move the rho out as well as the negative term, giving us simply dvx dx is 0. And this is an important result. It shows us that the velocity actually does not change in the x position, which is something we do want to confirm. This is the continuity equation of for parallel flow. It means that regardless of where we are in the x direction, right? If we have the tube here, we're here, here, here. Same y position though, right? Same y position. We know the velocity is going to be the same, which is something we want to confirm. That means we are on the right track. So that's step number 2. Now we're going to actually go to step number 3. Step number 3 is the conservation of momentum. Great. So looking at the conservation of momentum, we know that we have momentum, essentially dm dt, capital M. The rate of accumulation of momentum is momentum in minus momentum out plus momentum produced. We know we have these 3 terms. First, we do know that we don't have any accumulation of momentum. So that essentially is 0. So let's talk about each of these 3 terms. and what actually goes in those terms. So momentum in or out, and we're talking about in the x momentum, x direction momentum, we have two things. We have bulk flow. I'm trying to write this out in a better way. We have bulk flow. We have a bulk flow term, but now that we're actually looking at the microscopic level, we also have molecular transport. We have molecular transport. Great, I really recommend looking at my video if you have any questions. First, we do know bulk flow. We know that's rho Vx squared times the cross-sectional area of flow, right? And we know that since it's bulk flow in this way, it's the same as earlier. It's delta y times W, right? Delta y times W. On the other hand, for molecular transport, it's different. We use tau shear stress, tau yx times the cross-sectional area. But actually, the cross-sectional area, the momentum in the x direction enters through the y. So that means we're actually looking right here, the momentum we can think of as going in this way, right? So what is this cross-sectional area? Well, simply it's delta x times width. Great. So delta x times width, right? And then now we have momentum out. I want to specify this is at position x, and I want to specify that this is at position y. Great, and then for momentum out, we have rho Vx squared at position x plus delta x, right? We have the momentum going out here. So we want to specify that. And then we also have delta y times width. And then over here, really similarly, tau yx, y plus delta y. And then we also have delta x times width. So we have these terms so far. By the conservation of momentum statement, we're going to have a minus here, right? Since that's momentum out. That's momentum out. And then we have momentum in and the momentum out. So we can actually simplify this to be, I'm going to take the rho out too. We have Vx squared at x minus Vx squared at x plus delta x, right? Times delta y times W, right? Let me just move this down a little bit more. And then we also have plus tau yx at y minus tau yx at y plus delta y times delta x times width. Great, so that's for these first two terms right here. What about momentum produced? Well, let's take a look. So momentum produced, right? Essentially, that is just the forces that are acting in the x direction, right? And this, we also go over this in the video. But the rate of production is just the sum of forces applied in the x direction. We have two. Gravitational and then pressure. But actually pressure, C prompt, right? It actually gave us that pressure and this whole system is, changes are negligible, right? And then we have the gravitational force. Well, let's talk about that. So we have gravitational force as let me write this out over here. Gravitational is going to be, we have mgx, right? That's gravitational force. And for m, mass, we can use rho times the volume, right? That's what mass is. Density times volume will give us mass. So we can use the volume of our actual shell, which is delta X, delta Y, W, right? Times G, right? But Gx is actually in the sign, right? So it's not just G, it's going to be G sine theta. And why sine theta? Well, you can actually do some trigonometry. You'll see right here. That's the tube. And you can find the component of gravity that way. And you'll see that's sine theta. So please try that out on your own. So this ultimately is our last term. And to combine it all into one, we have all the way over here. I'm gonna copy and paste this. Copy and paste, great. Copy and paste, awesome. And then actually right over here, it's going to be minus, right? Not plus. This is not helping the system, right? We're going against gravity. We're going up when gravity is going down, right? So that's one also note to keep in mind regarding that. And if we're going up, or sorry, if we're going down, right? And gravity is going this way, that would be a plus, okay? Great, so now let's take a look at our conservation of mass statement. So we can recall from earlier that we said the conservation of mass, right, is 0. We have in equals out, right? So therefore, that means that this is actually going to cancel each other out. So that makes things a lot more simple. All we have are these two terms. And of course, I'm going to copy and paste it. Great. And sorry for the negative. That shouldn't be there. That was actually just from the copy and pasting. Minus rho. And then, I'm going to paste that right here. No, okay. Sorry about that. Having a little technical difficulty. Great, so now we have this. Now, same as the conservation of mass, what we did, the next thing to do is divide by our volume, right? Divide by volume. So that's delta X, delta Y times width, delta X, delta Y times width, right? And we can see right away these cancel out, and then these two cancel out, and we are left with delta Y. Then what we're going to do is take the limit, right? As X approaches 0, not X, delta X, right? The change. Our shell actually is delta X, delta Y, right? So we're trying to bring that infinitely small. So we have this, we have up here, we have tau yx, y minus tau yx, y plus delta y. Then we have over delta y minus rho g sine theta. Why isn't rho g sine theta in the limit? Well, that's because there are no terms with delta x, delta y, or with, or anything related to that. So we can just keep it out. It's unaffected. So now that we have this, we can take the limit. And as we know from earlier, this is just simply the negative derivative of tau, right? Tau yx with respect to y. So let's just rewrite that. Negative derivative of tau yx with respect to y minus rho g sine theta, right? And then now we're actually going to rearrange this. So d tau yx dy is equal to negative rho g sine theta. Now, the next step in this, so I'm just creating a new page, is to take the integral, right? We're going to move the dy over here. Then we'll take the integral of both sides. Then essentially we'll have tau yx equals, we have negative rho g sine theta times y plus c, right? This is key. And the reason for this is we still need to find this coefficient. We can't just leave this as is. It is relevant to this scenario. So let's keep going. How can we find C1? Well, actually, if we recall from earlier, I'm actually going to scroll up and show you in the prompt, it says right here, the shear stress exerted by the air on the mucus surface is neglected. That makes sense because on the gas-liquid boundary, right, interface, tau is negligible, right? So with that rationale, we can say, and at the interface, that's actually, so if we recall, we have this is 0, this is h, this is air, right? So that's at y equals h, So at y equals h, tau is negligible, right? So then that means we can plug it in. 0 equals negative rho g sine theta times h plus C1. What does that mean? C1 is equal to rho g sine theta h, right? And then now we can plug it back in. Therefore, tau is equal to, right? We have negative rho g sine theta times y plus rho g sine theta times h. That means we can rearrange and write rho g sine theta h minus y. And that is actually the shear stress distribution. Of the mucus layer, right? So that is the first part of this. Now, that is finishing step 3, right? Conservation of momentum will be your longest step. But after that, it does get better. So for the rest, I'm going to be a little bit more vague so that you can try this out on your own. But please look through my video on this, on the shell balance approach, and it will help a lot. So as we know, the fourth step in this is going to be to apply the relevant fluid constitutive relation, right? Now let's think. Let's recall from the prompt. The prompt gave us that the fluid is Newtonian, right? That means we're going to apply the relevant constitutive relation, and that is going to be Newton's law of viscosity. That is tau yx is negative mu times dvx over dy. And why is this important? Well, it's important because look, we actually do have tau yx right here too. So what we can do is set it equal to each other, right? Set these two equal to each other. And then that brings us to step 5, right? Find velocity profile. Well, we can find velocity profile because look, we have Vx. Vx is the velocity profile. So what we're going to do is set them equal to each other, right? Then we're going to essentially solve for dvx over dy. So you want something in this, right? Then you're going to integrate, right? You're going to integrate both sides like this. Then you're going to have something Vx equals something, but here's the key part. You're going to have plus C. You're going to have another coefficient we need to solve. Well, here's the good news, right? We know that this is about velocity, right? We're talking about velocity here. So what boundary conditions do we know? Well, the thing is, we don't have an actual no-slip condition here, but we do have at y equals 0, we have v0, right? That is what we need to solve for that c. So we're going to go back all the way over here. Sorry, should just put it back here, but we have Vx at y equals 0 is v0. And essentially this will be the key in finding C2. Then your answer for this velocity profile should be Vx equals something without any coefficients. You want to not have any of that. So that will be your answer, right? Now, step 6 is going to be to find flow rate, right? So finally, this is the last thing that's asking for just in part A. So we can find flow rate by first finding average velocity. Let's recall, average velocity is going to be 1 over h times the integral from 0 to h of Vx with respect to dy. So we're going to just plug in Vx from above, and then we're going to solve for average velocity. And then by doing so, once we have average velocity, we can just find Q. To find Q, that's simply going to be Q equals QV, QV, the volumetric flow, is equal to Vx, should I put X there, times the width times the film thickness h, right? And then you will be able to solve for the answer right here. Great. Now it's also asking for the velocity at the luminal surface of the mucus layer, right? That is just simply at y equals h, right? At the top of the mucus layer. So just plug with your velocity expression, right? You're simply just going to solve for at y equals h, and then you're going to have your answer here. Just plug in h for y. Lastly, for part B, it's asking, what is the maximum mucus layer thickness? And it's asking for the maximum mucus layer thickness that ensures velocity in all portions, right, must be positive. Well, let's think about this. So we have our flow right here, right? And we have V0 right here. And we're going against gravity, right? We can expect that we're going to have a decrease in velocity, right? And the thing is, at a certain point, when the thickness gets too much, right, too thick, we can actually start going into like negative, right? Where the liquid starts to go backwards. That's what we want to avoid. So the actual point at which the maximum thickness can be achieved is when velocity at the end, right? At the end of the layer is 0. So velocity here at y equals h is 0. That is the maximum thickness. And the reason for this, right, is h is just a variable. It's not like a given length, right? So we're trying to optimize this to have the maximum mucus layer thickness. And the way to do that is simply, we're going to plug in this right here into our velocity expression, to our velocity profile. So essentially, we're going to have our velocity profile, Vx equals blah, 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 right? We're going to plug in 0, and we're going to have plug in the y's, we're going to plug in h, because we're trying to find that maximum, right? And then we're going to solve for h. And then your answer will be h, something like that. Great, so that is the end of the walkthrough for question 1 of homework 5. If you have any questions, please email me. I'm more than happy to help you understand and get this homework done. So have a great rest of your night and see you soon. Bye.